Let's see how many. So we have Shira. I can see Vijay is there, and Pratim is Pratim there?
Yes, I'm here.
And then Ying, Ying is there?
Yes, I'm here.
Okay, so I think we have the full set of speakers here. So people who have questions, please go ahead. Yes, Rajit.
Yes, thanks. So I had a question to Bijay actually. The first thing is not a question. I mean, probably he knows that recently this no boundary proposal or sum over geometries in Euclidean path integral has been, shown to be unstable. I mean, it is shown 3 years ago that the path integral becomes unstable because there are growing modes, perturbations that dominate the path integral. So this baby universe, etc. There is some tension in that. So this is the comment. And the quick question is, what can we say about 4-dimensional ADS black holes and beyond ADS? Although there is no holographic setup yet established in the flat space, but there are some initial proposals, and whether one can compute this kind of, one can address this question of information loss puzzle, etc. in flat space.
Thanks for your question, Srijit. So indeed, there's clearly a wave of papers now coming out by a variety of people trying to apply these kinds of island formulae and their relatives to black holes in flat space and black holes in de Sitter space. De Sitter space, there were, well, with the positive cosmological constant, there were 2 papers this week, and there'll be one next week, myself and Tomonori and Arjun. So yeah, so the actual statement that was made, modulo this point about is the path integral with wormholes and what have you actually well defined, which is a question to be actually addressed. But modulo that question, the statement that including wormholes in the Euclidean path integral produces this sort of island formula, that's a general statement. It's not specific to ADS. It may be convenient to do some of these calculations in anti-de Sitter spaces, but in general, but that's a general statement. So, you know, there have been recent papers basically try to do that with flat space and with dilaton gravity and other kinds of things. So there's progress, but I think the verdict on the precise, consistent version of putting everything together is still out, as in the discussion with that we had with Prem a moment ago.
Okay, thanks.
Okay, so the questions from the audience, other questions? If not, then I'll ask a question to the complexity people, Shira and Pratim and Ying. So if we compute this complexity using holographic means, either CA or CV, even for empty ADS, we get a non-vanishing answer. So what does it mean? What is the reference state with respect to which this complexity is being measured? Do we have an idea of what reference state are we talking about in the holographic proposals?
So I think, oh, sorry, go ahead. Go ahead, sorry.
Shira, you can go ahead.
Okay. Yeah, so I think, well, I can give a few points. I mean, I think one hint that we have is that when we look at the way the complexity behaves, in particular at its structure of divergences, we see that there is a choice that we can make in the complexity equals action proposal related to normalizing the normals to the edges of the Wheeler-DeWitt patch, and that the place where this choice enters in the result is very, very similar to the place where the choice of the reference state comes in free field theory. So that might give you a hint that you have certain choices that you can make in the gravitational setup that encode the reference state. Another thing is that you might get a hint about what's the reference state if you study complexity of 2 states that are very nearby. So it's not my own work. So probably I cannot be like elaborate a lot about it, but there are papers by Ropp about the first law of complexity, in which they take small perturbations and they study complexity differences between states that are slightly perturbed from each other. And that's supposed to, I mean, if it depends on the perturbation quadratically or linearly, should tell you whether the trajectory between the states is aligned with the reference state that you're coming with from.
Nice.
So you can get some hints, but I think we are not there yet to understand extremely well. Another point of view that you might take is that this has nothing to do, like holography is not discussing a reference data that somehow I should adapt my prescription to depend on two states and to study distances between two states in a way that you might find more natural, because, okay, this unentangled reference state is a, I don't know, monstrous beast that lies outside my Hilbert space and we don't like it. So that's another approach that one might take. But I think, yeah, I mean, a definitive answer, I think we don't have yet. But maybe Ying has
Ying,
something to add.
Yeah, Ying, you were saying something?
Yeah, I just want to say, Shira mentioned some computations from CA. I want to say that we can gain some intuition from CV, especially some of the work of Brian Springle. He discussed the mirror tensor network. And in this case, he basically showed that ADS geometry roughly correspond to a mirror tensor network. And if you ask what this mirror tensor network does, you see that it basically builds up the entanglement scale by scale. If you start from some completely, say, unentangled state, say just a line of qubits, and then you first, say, entangle the neighboring sites, then you block them, then you entangle the neighboring sites again. And this kind of tree-like structure actually corresponds to ADS geometry. If you really have empty ADS, you can just continue indefinitely if you have infinite line. And that corresponds to, say, Poincare coordinate of ADS. But say if you have at finite temperature, you have to stop somewhere. Once you reach the thermal scale, and this corresponds to, say, cutting out the space-time at the black hole horizon. So from this point of view, it looks like there's a pretty good match to see that if you really want to ask what are these quantum circuits doing, looks like they are sort of building up the entanglement at different scales.
I see. So naively speaking, if I take the CV at face value, yeah. It tells me that the complexity will become zero only if the volume is zero.
Yeah.
So is it fair to say that this reference state is something which doesn't have a geometric interpretation or doesn't have a space-time interpretation? Reference state is something which is...
It's really simple. Simple naturally. Just one guess is, in this case, from CV is product state without entanglement.
I see. Okay. Okay, Pratim, do you want to contribute to?
I have one question for Shira. If she can shed any light on something. I noticed during her talk she made some mention of a quantity called VTH, which was the thermofield object. So, is there any way you can extract temperature dependence of a mixed state complexity from that object?
Can you repeat which object? Yes, I can tell you about the temperature dependence of complexity, but can you tell me, I just didn't catch what you were saying. Which object? Did you say thermofield double?
Yeah, so thermofield double, during your talk, you had some expression which was e to the power minus beta of something, which you were tracing out to get a pure system. Now, could you extract some information about the temperature from that from those expressions? So basically, what I'm asking is simple. For a finite temperature system, can you extract some information about the temperature dependence of complexity?
Yeah. So the answer is definitely yes. You would have to look at some finite subtraction. I told you that complexity was divergent, but you can take the complexity and construct some finite quantity out of it. For example, if you take the thermal state, the complexity of the thermal state, which has a very large component, which is just divergences of the short length scales, and you remove the vacuum. So you subtract that, you will be left with a finite quantity. And that quantity will be proportional to the entropy. So temperature to the relevant power.
I see. So more or less, I think what you're referring to, the finite part being proportional to the entropy, is something I referred to briefly in my talk, right? The finite part of the complexity being proportional to the entropy.
Right.
So you get a similar result from field theory, I think.
Oh, I see. Yes, the answer is yes. Sorry, I didn't realize you were asking about QFT, but yes, the answer is definitely. You get for the what you would call the complexity of formation, you get a result which is proportional to the entropy.
Yeah. So another question, if you don't mind. So I also had some results about that structure breaking down in more complicated setups, right? Mutual information, like two disjoint intervals. Yeah, so could you comment on that picture from the field theory side? I mean, what you're saying, that the finite part of the complexity is proportional to the entanglement entropy. Is that, I mean, how universal is that result? Because there might be scenarios where that picture breaks down. Could you comment?
Yeah, let me think. I mean, well, I can tell you that we looked at, I wouldn't say that we tested the whole scenarios of the world, but we looked at, subregions of the vacuum where we found that this was the case. And right, that the mutual complexity was proportional to the entropy. So that was for, a subregion and the complement, which is not two disjoint intervals. And I'm not sure that I know something very smart to say about disjoint interval. There might be something, and there is a paper, I think, of Elena Kacheras with like students and colleagues that has a similar statement, and maybe they mentioned disjoint intervals, I'm not sure. And in the field theory setup, in the free field theory, a subregion of a 1+1 dimensional lattice in free field theory. I mean, I think we conjectured that it was more general, but we don't have like a proof or something of this kind. It's just that, when you look at the vacuum, especially in holography, there are not that many numbers there. It's all the central charge. So at the end of the day, things should be fixed in terms of each other, at least when you don't talk about dynamical situations. And that's why I said, if you remember, someone asked me in what complexity was special, and I said that I think you start gaining real advantage when using complexity when you talk about dynamical situations. I don't really expect the complexity of the vacuum state or a static situation to have a lot of new information necessarily.
I see. Thank you.
Okay. So
maybe I can actually ask to Vijay. I don't know if he's still around, but are the speakers allowed to ask a question as well?
Yeah, sure. Go ahead.
Yeah.
So I wanted to ask you in general a little bit, because many of the setups are, static. The setup that you were presenting to us, that was like slightly more than half the BTZ patched with slightly more half BTZ. I was just wondering, like, what is flowing between the two sides? Is there, information is flowing, but is energy flowing between the two sides? Is it really evaporating? I mean, it's a question that I have about many of the constructions.
Absolutely. So this wasn't a dynamical setting. So we didn't allow, I mean, you could imagine constructing this geometry, it's a solution, with the brain, it's a solution, and you could send stuff back and forth. No one's done anything like that, and study the dynamics of this thing. So the confusing thing is the way in which the evaporating protocol is set up, right? Because it's supposed to be like evaporation, but what does that mean? So in several of these papers, as you know, and as you're alluding to, you basically imagine this kind of static E situation where you have a system that's come into equilibrium with K quanta. And then by hand, you increase the number of quanta K and make it bigger and bigger and bigger and ask what happens. That's not the same thing as a full, obviously it's not, clearly it's not the same thing as a fully dynamical setting. And it would be better to have a properly dynamical setting. There've been some efforts that I'm losing track with all the papers that have come out. Maybe this is one of Don's papers. I can't remember exactly whose paper it was, in which, you know, you imagine that the radiation actually goes out, but then to keep the thing in equilibrium, you have to send radiation back in from the reservoir. And, you know, there's been some analysis of that, but kind of the clean setting clean, I don't know if it's clean. The setting in the toy model in which people have been making progress is this taking this number K and just simply increasing it, right? So there's no dynamics there. So this is why I actually like this, the thing that I mentioned at the very end, which is the toy model that I've been working on with Tomonori and Arjun to keep it completely clean. I mean, there really is no dynamics. I have a universe with a certain number of quanta in it, a certain number of degrees of freedom, and contains gravity. Another one just doesn't. It's not a matter of radiation, right? It's a matter of, you know, you have this system and have that system, the kind of thing that we would do in a quantum mechanics class. I've got two boxes, right? And then I ask myself, this has so many degrees of freedom, that has so many degrees of freedom, and I keep increasing the number of degrees of freedom to be very, very large, let's say on one side, and I entangle them. Well, surely quantum information rules tell me that the amount of entanglement entropy on this box where I'm carrying, you know, other degrees of freedom can't be greater than log the number of bits in this gravitating system. I mean, surely not, right? So how does that come about, right? So so I think you can ask that. So the question of the underlying question of preservation of monogamy, I think, can be asked without dealing with the complications of the Hawking radiation, the dynamical emission and stuff like that. So that's what I was trying to say in that little toy example. And I think several of the methods of, you know, having the evaporation protocol in equilibrium with, you know, K bits in a reservoir are basically, that's what they're trying to do. They're trying to distill away the part of the problem, which is monogamy, without the complications of the Hawking radiation. So the short answer to your question is there is, in these models, there is no explicit dynamics, and of course it would be better to have the dynamics in. Did I answer your question?
Yeah, and I have another one. So just to try and understand like the nature of the way the two theories are coupled. So imagine that I didn't start in a situation that was really balanced, and I would.
Are you sorry? Which two theories? You're talking about the first part of the talk where there's this end of the world brain and there.
Yeah, exactly. Yeah. So I want to move. I don't know. Imagine that I started with a setup that was a bit asymmetric to black hole with slightly different temperatures, or I'm not sure if you can patch.
I mean, but that is how it starts out, right? Because you have the one black hole. You have the end of the world brain, and the end of the world brain is in a thermal state depending upon how much entanglement it has with the Hawking radiation, if you like, with the radiation. And therefore the temperatures are not going to be the same on the two sides.
I see, but eventually the end setup it looks completely symmetric. Is it an illusion like the...
So it's not completely symmetric. It's not completely symmetric because...
I see.
Right, it's not symmetric because, you know, the end of the world brain has a certain central charge, it has certain properties, it has whatever thermal density matrix you get by tracing out the radiation. And so on the sort of, when you do the holography for it, on the what we call the inception side, which is a reference to the movie Inception, you know, so if you, so on that side, you know, everything like the central charge, the G Newton, the size of the black hole horizon, the temperature is all determined by whatever the properties are of the end of the world brain. And this may or may not have much to do with the original, you know, the original BTZ black hole. So it's not symmetric, which is why you have to be careful about making sure that you have a splicing, you know, Israel junction conditions, how you choose the stress tensor on the brain, things like this. So it's not symmetric.
I see. So then, like, if it's not symmetric, like, why wouldn't I expect energy to be flowing between the two sides? Like, if I have a black hole at one, I could.
You could.
And do you know anything about I promise this is the last one, but do you know anything about the nature of how energy would flow? Meaning if I would like send the propagate some kind of perturbation from one side,
I think this is what's
the way how much is passing depend on the energy of the propagation.
So let me give, that's a very good question. And let me give you a fantasy. So back at the dawn of time, when D-branes first began to be used as a description of black hole microstates and everything, let me tell you what my own personal fantasy would have been, right? I thought, oh, great, wonderful, right? So what happens is that you have this thing that looks like there's a black hole throat, all the horizons and everything. The way I get to the D-brane picture, I take G string or G Newton and make it very small. And so what happens is that the horizon shrinks, of course, it's proportional in size to G Newton. And eventually the horizon is string scale. And really I can think about the system as some collection of D-branes sitting there. Okay, so in the back of my head, I used to think, okay, so what happened to the region behind the horizon? Oh, well, that's the dynamics of the D-brane, right? So somewhere in the dynamics within the open strings in the D-brane, I used to say to myself, live all the microstates and live the physics behind the horizon, okay? So I used to think at the time that the way in which somehow we would finally solve all our problems with black holes is we would think, okay, I have this D-brane, system of D-branes, I send in a quantum from outside, it hits the D-brane, goes into the D-brane, merges out, and does whatever it has to do, and that's the story, right? And then as you increase the coupling, there's some nice gravity description of this. Now, of course, ADS-CFT is a version of that. That's very beautiful, wherein you have the flat space outside, you send the quanta in, they enter the D-brane, but that's really dual to the whole ADS throat, and then you stick stuff there and it comes out. Now, now I think what we are now, in my opinion, what we are now creeping up towards is a second incarnation of that, where we now imagine that behind the black hole horizon, indeed the black hole microstates are made from some D-branes. And what you're really talking about, in my opinion, is I send the quantum in from outside, and it gets into the D-brane, and it does whatever it has to do. And I think the picture we were trying to describe is, suppose that D-brane system itself has its own separate holographic dual. So what you want is to say, well, the thing goes in the D-brane, does what it does, but there's a holographic dual description of that. It's like doing ADS-CFT for ADS-CFT, the second one there. So I think this is a question that can be asked and should be asked, right? Stuff comes in, falls in the black hole, in effect merges, if you like, into the Higgs branch of the dynamics of the D-branes. That has a dual description in this other space. That's what we're trying to do. So I think it's an askable question. We just need to find a scenario, either a toy model or a sufficiently controlled scenario where you can calculate. I think it's a very good question and worth thinking about. We haven't thought about those things for some years now because there have been other questions to answer, but I think it's time to ask that question again.
Okay, we have a question from Aranya.
Yeah, thank you. So I have a question for Shira. So you mentioned the complexity of purification calculations regarding complexity of black holes, right?
Right.
Yeah, so or more generally mixed states. So due to the recent developments in the CFT side of complexity, the papers that have been coming out since last 2 or 3 months or so. So do you have any idea how to deal with, say, mixed states in CFT, or get a better idea from the perspective of CFT and then match it with black holes?
Yes. So I was not like super elaborate about the holographic side of this in my talk, but definitely, I mean, you can look at mixed states. In the holographic setup, usually this would be by looking at a subregion. So, usually you would have a geometry that is dual to the full state, and you would focus on a subregion of this geometry in which the state is mixed. And there are proposals for when I take a geometry that describes a state and I focus on a subregion, some proposals that are basically motivated by the fact that you think that the reduced density matrix of the subregion is encoded in the entanglement wedge. So the proposal is to look at a minimal surface that anchors, to look, say, in the following way. Within the maximal surface of the volume proposal, look at what is the portion of the volume which is enclosed between the boundary and the Riuti-Kayanagi surface. So just a portion of the full slice volume. And you can definitely do that for example, the famous example is I have an internal ADS black hole, which is dual to the thermophile double state. And that's a purification of the thermal state. So in this case, if I focus on a single boundary, I'm going to have the thermal state living on a single boundary, and then I would be studying surfaces that end just on one side. And when you do that, you will find all those same properties of the divergences, for example, as I was saying in the CFT side. So you would find that the thermophile double is twice as divergent as the thermal state, which is intuitive, because when you study complexity of purification, there is a much more efficient way to build a thermal state using an extra doubled set of degrees of freedom, but without actually manipulating too much the second set of degrees of freedom, without making all this effort to create like mimic vacuum correlations on the other side, which you would be doing if you were really trying to build a thermophile double state. So you see it both from field theory and from holography, this, I don't know, this kind of argument of if I'm building the thermal state by building the thermophile double, I'm working twice too hard. This is something that you can see on both sides.
Okay. So another question that I have is, so given the recent development in the CFT complexity calculations that Hiller and Mario Flori they did, so could I do a similar, say, complexity of purification calculation taking up CFT states purely from the CFT side, developing on what they have done?
That's a very good question. I don't know the answer. I think that's really interesting. I mean, I don't know actually how it, let me think. I mean, of course, we know in CFT language how to treat subregions, right? We usually do it with replicas. We put twist operators at the end of the subregion. I mean, there must be something. That's a great question. I don't know. I think that would be cool.
Yeah.
Okay, so anyone else? If not, then
I have a quick question actually regarding this PEDS map to ING. So at the last part, when you actually talk about computing complexity of this map on the PEDS map operator, so you basically compute how the size of this U operator is growing at the time, and then you are saying that the complexity is basically that how this size is growing.
Yes.
But instead of doing that, is it a reasonable question that I take that U dagger as a composite operator and compute that complexity for that operator using this Nielsen method? That is by doing a geodesic analysis by connecting identity to this operator.
Yeah, that would be great. It's the problem is with the Nielsen's approach is that the Nielsen geometry is very complicated. So far, we never really solved Nielsen's geometry. But what you proposed actually works in a sense that there was a easier toy model. If let's say we don't take Nielsen's geometry, but we just take a surface with constant negative curvature, and then this UWU dagger looks like something like this. This is U, a geodesic, and perturb a little bit, then go back. And then you can ask the geodesic distance between the two ends. This computation, reduce a problem to a geometry problem. And this was done before. And indeed, we see kind of all sorts of a switchback effect. Start from exponential increase to linear increase, switchback. But it's not done on the full Nielsen geometry. Another thing is,
but that is almost similar like this Loishmi-Deco type of business.
Yes, that's exactly it. But another thing is that only works when, say, U is the K local. So that works when if you want to do this kind of reconstruction, you keep the entire system. That works. But if you only say you have part of system, there's Python's long trip here, whatever. So far, all we have is some circuit analysis.
I see. But is there any example of this construction of this map for some spin chain model? Maybe that may help. Like
for some what model? Sorry.
Spin chain type of model, something like that. Like spin chain. Can you construct this map, this operator for some spin chain, like SU to SUN spin chain?
Spin chain.
Yes.
Do you mean doing PEDS map or doing look at this?
I mean the PEDS map.
The PEDS map.
Yes.
I'm not expert on this. I don't know. But I assume the similar construction. I mean, the PETS map is, initially when it was given, it's a complete quantum information construction. The key is that there's they assume various properties, quantum information properties, and that needs to be satisfied.
Oh, I see. I see. Yeah, thanks.
Are there other questions?
I think one question is on the chat.
Yeah, I noticed that.
Maybe you can, if he's there, he can ask that.
I don't see the question actually. Is it?
You can ask him directly. This Mo.
Oh yeah. So this is again regarding the PETS map, which I'm just trying to understand this construction. So again, I'm referring to the old HKLL construction for exterior operator, where you have a very nice construction in which the size of the smearing region is equal to the depth at which you place the operator. This radius scale duality, which is completely manifest. And then when let's say you reconstruct an interior operator using this PETS map, is there a geometric picture of this in terms of a smearing, or or is there a geometric way of understanding what this interior operator is?
If you want to talk about this smearing, I think what happens is this. It's throughout this construction, when we talk about interior operator, we assume the S qubits. The boundary degrees of freedom is the number of boundary degrees of freedom of CFT is infinite. It's not S. So what happens that you do kind of a smearing to first go to the horizon to reduce the number of degrees of freedom to S, and then there is a quantum circuit happening on these S qubits, which you can say that basically it's related to the horizontal circuit is related to wormhole geometry, and you undo that part. So we didn't include the smearing, but imagine, I mean, it's what we did is at the end of the day, we have an expression of the operator in terms of S qubits, but at the end of the day, you need to write this S qubits, the operator on this S qubits in terms of a boundary operator, then you need to do this kind of smearing.
I see. So there's no continuous way of deforming the HKLL construction to the interior. It's like, it seems to me that it is completely.
Yeah, I guess it's the fact that if you look at HKL reconstruction, the complexity blows up. That signals that something needs to happen.
So the breakdown of the description, basically, that it's not a good. I see.
Yes.
Got it.
That you can still do that, but you need fine-tuned knowledge, and there will be state
Right.
dependence. All sorts of things come out.
Sure. Okay. Thank you. Okay, I think we don't have any more questions. I think we can.
We are almost time actually. So maybe.
Yeah, it's almost time. 9:40. We're supposed to resume with Frame's talk.